Hey everybody, it's Norm from Tested.
And Frank from Tested.
We're down here at Frank's shop this week for a really exciting project. I want to introduce you guys to Drew, who's from a company, CNC Router Parts. How you doing, Drew?
Great.
Thanks for coming down. You guys are based in
North Bend, Washington, just outside of Seattle.
Outside of Washington, but we met you guys first. Frank and I met you at Maker Faire this year, where you guys caught our eyes because you had the booth where you guys make CNCs.
Like multiple booths.
Multiple booths, and you guys were giving away crossbows.
That's right. It was a really fun project. We got to make all the parts of the crossbow on all our machines there, and then give them away every 30 minutes. So
that's super cool. And we got in touch with you guys, and now you have sent down one of your machines, but it's not built. It's actually on the floor right now.
All knolled out.
So you guys make CNCs.
We do. We make CNC Machine Kits. So we make full CNC Machine Kits, everything you need to put together a machine with a 4 foot by 2 foot, 4 foot by 4 foot, 4 foot by 8 foot work area, anything you want. We have customers who've gone as large as 6 by 16, all sorts of stuff.
And what type of heads can you put on this?
So it's a CNC routing machine. So you can use a router like the one you'd buy at Home Depot and mount that to the machine, or you can buy a 2.2 kilowatt air-cooled spindle, and that's what we're going to put on this machine. And also on the machine we're going to build here in your shop, it's going to be half plasma cutter, so it's also going to have a plasma cutting torch.
Wow, that's a lot of versatility, and the one we're building here
very exciting.
Is going to be a 4 by 8?
4 foot by 8 foot work area total, but we're going to set up so that 4 foot by 4 foot of it's dedicated to plasma cutting, and then that's the other half, the 4 foot by 4 foot in the front, will be for routing.
But if I ever wanted to route 4 foot by 8 foot, I could take the water table off.
Exactly.
The whole table.
That's right.
So what we're going to do today is put together this machine. It's going to require a bunch of assembly, a bunch of electronics, and then we're going to have you walk us through the process to actually build some things at the end of the video. So I guess it's time to get started.
Let's build.
Okay, Drew, so about 4 hours of building into this CNC. We got a table, it looks like.
Yeah, that's right. So from the parts that we had laid out earlier, we've now got a nice and rigid extrusion-based frame construction, and it's all complete at this point. So the next step will be for us to get our risers all set up and install our gantry across the risers, and then keep going from there, get our x-axis and our z-axis in place.
Absolutely. So this is a good time. I want to talk about like the design of the CNC, because you're a mechanical engineer. You help design, like maybe not exactly this system, but parts of this system.
Absolutely.
And you guys, from scratch, think about how to make CNCs that are scalable. So this system you guys sent, it says 4 feet across.
That's right. It's a 4 foot work area. It's a little bit larger than that, the physical dimensions, outer dimensions, but 4 foot work area in the width, and then about an 8 foot work area in length. You actually get a little more than that just to ensure that you can get to all sides of a 4 foot by 8 foot piece of material.
And then you have models that could scale, that could be 4 feet by 4 feet.
Absolutely. That's one of the big advantages to a machine like this that's based around extrusion, is that if you want to, you can start out with a smaller machine like a 4 foot by 4 foot work area machine, and then decide later that you want to upgrade and expand that work area out to 4 by 8 or 4 by 12 or 16 or however much work area you need.
Right, and then the design of this table, like this thing is solid. It's not moving around. What are the important things about making this work as a CNC surface?
Right, so these anchor fasteners actually have a lot to do with the rigidity of the table and all the cross members. So anchor connections are one of the strongest ways to join extrusion together. And they're going to keep the frame really, really rigid and really square to itself. And these gussets also help reinforce the frame. So during movement, inertial loading, there's no way that it's going to flex or twist and get thrown out of alignment.
Yeah, and it felt like that was the most stressful part of putting this together, getting these braces across, aligning them. You have jigs that you brought to have them perfectly lined. Let's talk about the drive system.
Sure.
So we built some CNC, smaller ones that use like a belt system with stepper motors. This is a pretty big stepper motor you have here.
That's right. So this is a NEMA 34 frame, 960 inch stepper motor, and it's driven through a 3.2 to 1 reduction to this pinion gear that interfaces with the gear rack. So that's what allows us to get some really high speeds on our gantry travel. And then in order to eliminate all the backlash that you see with rack and pinion systems, there's a nice tensioner here that once you crank down on this big spring, it's actually going to drive that pinion gear up into the rack and allow it to sort of ride the rack, any sort of angular misalignments or any issues like that. That eliminates any sort of play in the system.
And this gear rack here is 2 pieces on this size. We had to do some alignment to make sure that it actually fits, but that was what makes it scalable.
Right, exactly. So because the gear rack is it comes to you in chunks, it's easy to get through your door into your garage or your basement, and then when you put it together, if you want to later add on more length to your machine and expand that work area, you can just keep adding more chunks of rack in and align them with that jig.
Wow. So as a mechanical engineer, you work in CAD, you're designing these plates, the system. Like, tell me, how do you end up with like this type of design?
Sure. So the design of this riser plate is swept back like this to try and keep the lever arm, the cantilever, as short as possible when you're actually looking at the tool, engaging the workpiece. And that you'll see that later once the gantry is assembled. But basically, we want the tool to be as close as to the center of this plate between these 2 linear bearings as possible, because these linear bearings are really what are giving us the torsional rigidity and just the overall stiffness of this interface is all through these linear bearings, which have a really, really high moment load rating and load rating in general.
And what's like your priority, your criteria when you're designing something? Because would it be this design if you were building something smaller, if you didn't need to move as fast, need to have as fine control, if you're using a different drive system? Like, these are all made for CNCs like this scale.
Right, so a rack and pinion system is a drive system that has a lot of advantages for longer travel machines and also machines where you need to be able to change the length. If we wanted to make a smaller drive axis, like on our Z-axes, we might use a ball screw, which is a really, really stiff, really low backlash system. But you have to worry about things like screw whip when you start to increase the speeds. And it's also a fixed length. And so that's one reason why we might choose this drive system over a ball screw for this application.
All right, and that Z-axis is the next step. We're getting close, maybe another couple hours before the physical assembly. Let's get to it.
Great.
Okay, Drew, so we're in day 2 of this build now. The clothes have changed. You're still wearing the company uniform.
Absolutely.
So how far are we along with this, the mechanical part of the build?
So at this point, most of the mechanical assembly is complete. Before we talked about, we had the whole bed and the risers assembled, and now we've got the gantry installed as well.
So it's a 3-axis machine, and you guys think of the bed here, what we did first, that's the Y-axis.
That's right. So as you're standing in front of the machine and looking down the length of it, as the machine moves away from you, that's your Y-axis. So as the gantry travels, your X-axis will be the plate here moving back and forth along the length of the gantry, and then your Z-axis, your up and down motion is going to be these 2 Z-axis assemblies here.
Right. I'd love to talk about the drive system a little more, because that stuff is super fascinating.
Sure.
In the previous CNC machines we've built, and even the 3D printers we've built, they've all used stepper motors with different type of drive systems, belt systems, screw system, lead screw systems.
Chain drive.
Yeah, chain drives.
Sure.
So along the gantry here, that's the X-axis and the Z-axis. The X-axis, is that the same drive system as the Y?
So the X-axis is basically the same drive system as the Y. It's got that same rack and pinion drive setup with the gear rack along here, and then the pinion gear and the NEMA 34 motor with the 960-inch torque rating, and a tension bracket to keep it pinned up against that rack to eliminate any sort of backlash.
Right.
The Z-axis is actually an entirely different drive mechanism altogether. So that's going to be a ball screw. There's a lot like the lead screws you've seen on your 3D printing machines.
Oh, I remember putting those 3D printers together, get 4 lead screws, got to calibrate those nuts, get them aligned, yeah.
Right, exactly. So it's a lot like a lead screw, except that on a ball screw, there's going to be a ball bearing nut that's going to be preloaded against the screw, and that's going to eliminate any sort of backlash.
Huh. What do you mean by backlash?
So backlash is what happens when you're moving one direction and then stop and change direction and go back the other way, and you lose a little bit of your position. There's going to be some play. and that's going to eliminate any sort of accuracy you'll have in your workpiece. So to get rid of that, if you preload the ball bearings inside the nut against that screw, it can't move around, it can't jostle back and forth as you change directions.
Right, and that's going to be a big consideration because you're moving at pretty high speeds here.
Yeah, so we are moving at pretty high speeds, but notably, a ball screw, like we talked about earlier, wouldn't be great for this long axis because you can't change the length. And as you increase speeds, you're going to worry about things like ball screw whip, right? But on a shorter axis like this, they're very high precision and very quick.
Oh, very cool. Now, the other thing that people might notice is that there are two stepper motors here along that Z-axis because it's a two-head system. It's almost
right.
like in 3D printer parlance having a dual extruder.
It's a lot like that. Yeah, that's right. So we've got, in your instance, you've got both a plasma cutter, which we'll mount up later, and a spindle, like a 2.2 kilowatt air-cooled spindle with a reciprocating tool to cut away from material and mill out your workpiece.
Now, could someone build this system and if they didn't want to use the plasma cutter accessory, put two spindles on there?
Absolutely. You could mount two spindles right next to each other, and that way you could maybe mount your roughing tool and your finishing tool, and then do the whole thing in one pass without having to change tools or walk up and mess with the machine.
And that's just in that CAM process, just designing that work path in there.
Yeah,
that's
right.
very cool. That's very exciting, and that's why I guess the gantry needs to be a little wider.
So the gantry is a little bit wider than normal on our 4 foot by 8 foot travel machines, and that's so that each of the heads can get all the way to the outer edge of the bed.
Okay, so mechanical assembly, mostly done, of course, the actual two heads need to be put on there. What's in store for today?
So today we'll mostly be running cables, so there's going to be a controller that sits right down here, and all the cables that connect up to your motors and sensors are going to run from that controller through your cable trays and your cable track, and then up and around to all the various places that there are motors and sensors on the machine.
The motors, the muscles of the machine are in. It's really now the brain and that nervous system.
Exactly, exactly.
Okay, Drew, I think you told me this is system ready. It's ready to go.
That's right, we're ready to go. We finally have all of our motors plugged in, all of our inductive limit switches and homing sensors wired into our control box, where all the control electronics are, and we're hooked up to our laptop.
I mean, a lot has changed since we last checked in yesterday.
That's true.
You did not only the wiring, but also the two heads are on.
Right.
You have a Z-axis and it's...
Right, so we have a spindle motor here, which is for our 3D contouring, our routing out of aluminum, softer metals, plastics, woods, and then we have our plasma cutter, which is for cutting sheet metal, so steel and also aluminum sheet.
And one's the Z-axis, one's the A-axis?
Right, so we define the three ways the machine can move the three axes of motion as X, Y, and Z, and then your secondary Z is in the software is called your A-axis.
And can move independently of
right,
the Z-axis.
exactly. So we can jog either one independently, and this machine is just a way to position some cutting tool, some implement somewhere in 3 space, right? You know, in Cartesian coordinates. So in this instance, it happens to be a spindle and a plasma cutter, but like we talked about earlier, you could do 2 spindles or 2 plasma cutters if you really desired.
Right, and what people might notice also is there's a Vac System.
That's right, so we rigged up this dust collector, and that's helping to pull up all the chips and all the fine dust, especially when we're cutting materials like MDF, which throw off a lot of particulate.
So you can't currently see.
So I'll jog that over here and we can take a look.
Oh, look at that smooth movement.
And so this dust shoe just has a strip brush on the bottom, and that corrals all the chips right next to the air hose here and pulls them all up and out of the way.
Is it magnetized?
Yep, so it's got magnets that hold it into place right there.
That is so sweet. Now you did some calibration. Can you talk about that process? How important is it to get this square, level, so that the machine knows where your starting point is, where your origin is?
Right, so you not only need to know where your origin is, but you need to make sure that the machine is square to itself. So when you put a workpiece on here, if your table is slanted somewhat with respect to your spindle, then the part that comes off the machine is always going to have some inaccuracy, so it's always going to have that angle built in. So to eliminate that, we do some calibration procedures when we first get the machine set up. And also, of course, you want to pay attention when you're assembling the machine that everything stays nice and square and true. But after you're done, we put some parts on the table and do some test cuts, and you can see in the test cuts, and if you take some measurements, whether or not the spindle is out of tram, which is back and forth this way, or out of adjustment in and out of the gantry itself.
What are you noticing in those test cuts?
So what you do is you make a box where the step over on the tool is about 90%, and then if you have a machine that's significantly out of tram, you're going to see these really defined ridges where the two passes meet, and then you can move the spindle back and forth. And there's actually a couple of easy adjustments here with this big bolt you can put a wrench on and turn, and that'll allow you to really dial in that tram. And then we shim the spindle back and forth to get that dimension totally squared up. We also want to make sure that the whole gantry is not racked one way or the other. And so the way we deal with that is these homing switches. When you home the machine, it's going to drive all the way into the front left corner and find these inductive limit switches, and then that's its home. And if the machine is racked at all, you'll see that in the test cut, it'll be more parallelogrammed than square. And so we can adjust the position of these sensors, and that will adjust where the gantry actually stops. And by doing that, we can get it to be totally square.
So there's a whole calibration process. And you actually did some first test cuts to make the waste board. So there's 2 layers here. MDF on top, what's on the bottom?
So on the bottom is HDPE. And the reason we chose HDPE for this is we're going to be doing some plasma cutting back here on our water table. And that water table, when you plasma cut, sometimes you get some water that splashes out. And we'll have a cover for this, MDF when we're cutting on the water table on the plasma cutter. But you know, if you need to replace your MDF, it's no big deal. But it's nice to have a fixture board underneath that's resilient and won't absorb water, and you can surface and then leave in place. It's a more permanent solution. We also put in some clamp holes in the HDP, which I think you'll see. And we have some insert mounts as well, so you can quickly and easily swap things on and off and bolt things down.
Yeah, clamping is this whole different system that we'll talk about in terms of the experience you need to work a machine like this. So you might understand that this goes away when you want to put like a 4x8 on top?
Exactly. So if you want to do a full 4 foot by 8 foot sheet and just do routing only, then it's pretty easy to take the water table off. It's just these brackets on either side, drain the water out, and the whole thing will lift right off, and you can get your full sheet on.
Wow. Let's see the machine move again, because I'm impressed by how fast it is, how responsive it is.
And then you can go down and up on your Z-axis, and independently on your plasma.
I love that each of the stepper motors has its own frequency. You can like, hear the song of the machine
the whine,
sing. So I guess it's time to do a project. So let's jump into a project.
Sounds great.
Okay, Drew. So you guys have come up with a good first project to test this table.
That's right. So we're going to cut out a chair that uses both wood and metal parts. And it's actually originally an open desk design. But the original design called for a seat that was made out of plywood and was cut multiple times to allow it to bend. It was really challenging because you had to have plywood that was perfect with no voids or any errors. So we decided to take our own sort of spin on the design and make a metal seat instead with the same sort of feel. So there's a lot of perforations that allow the seat to contour.
Oh, very cool. And that's a great time to talk about the workflow, because there's CAD, of course, to model everything, but this is CAM. This is designing tool paths.
Right. So for a machine like this, you need to have a 3D model, like you said, in the CAD side of things. Then you also need to tell the machine exactly how you want to cut out those pieces from your raw stock. And that's the CAM side of things. So in Fusion, we've got our model here we've imported, and we've moved it around so that we can fit all of our parts on a couple of different sheets. And then we can go over to the CAM side of Fusion, and we can look at our tool paths that we've created. So,
wow, so it's one system in Fusion. You're just
yeah.
swapping using the same model data, the same meshes, except now you're telling it to output different instructions.
Right, we don't have to export or import anything, it's all just in the same interface. So we swapped over to CAM now. You can see our first sheet has all of our legs for our chair, and I've defined all the different drilling operations we're going to use to put all the dowel holes in, and that'll allow us to reference the two parts together when we glue them up. And then we've got...
And that box you had before, that's the size of the work material.
Right, so that defines our raw stock, and that's a really great way to visualize where the parts are on the table and whether or not it's going to fit inside of the stock we're going to be putting down.
It's like using a laser cutter and fitting everything, all your vectors around.
Exactly. So we'll do that drilling first, and inside of that operation we define our tool, our speeds, and our feeds, which are important for good cut quality. And there's a lot of other parameters in here that allow you to really take full control over how the machine is getting this part out of your material. The next thing we'll be doing is this contouring operation, which actually cuts all the legs out, so it separates them from the stock itself. But notably, it's going to leave these tabs here so that they don't come out too early before we're ready and end up chattering around and ruin the workpiece.
Right, because there's a lot of force going around with the spindle head.
Right. As the spindle is moving around, that end mill is going to be exerting quite a bit of force on both the workpiece and the remaining stock, and you want to make sure that the part doesn't move around on you.
Yeah, misaligned.
Right. So then you've got your second sheet here that will have the remaining chair parts, and it's got a very similar workflow. We'll do our drilling operations first, and then our contour passes. And then our third part here is our steel seat. So we've got some sheet metal we'll be cutting out, and you can see we're going to do all these pierces, and that's going to allow us to bend the metal really easily and kind of form it into that nice sculpted seat shape.
Yeah, you're already using different terminology because this is with the plasma.
Right.
Yeah, it's piercing through the metal.
Exactly. So in plasma, you don't have to define anything about how fast the spindle's rotating or anything like that. You're really just defining the path for the plasma cutter as it's traveling around and flash melting through the steel.
Do you have to let the machine know how thick the material and that
So-
you're using steel versus any other type of metal?
Right. In plasma cutting, feeds and speeds, the analogous thing is how fast you're cutting, how fast you're moving, but also your arc voltage and your amperage. The amperage is something you're going to set on your power supply, and that's going to remain constant the whole time. The arc voltage is actually a function of the distance from the torch tip to the workpiece. And that distance is what ensures a really nice, clean cut with low dross. So if you see a lot of hand-cut plasma parts, a lot of times there's a lot of dross and the cut doesn't look very good. And that's mostly because it's very hard to keep a consistent work height and a consistent arc voltage by hand. But the machine can constantly vary that distance, and it actually monitors that arc voltage and is adjusting in real time to make sure that you have that perfect ideal voltage.
Micro elevations
Exactly.
in that A-axis as it's moving along. That's amazing.
Yeah, and that's called torch height control. And it's a big part of why our electronics package for a plasma cutter is different from our regular electronics package that only does CNC routing.
All right, now walk me through how we're going to mount the work material onto the wasteboard.
So for the chair, we're going to be putting Baltic birch straight onto this MDF. And there's lots of different ways we could hold it down. We could clamp it or we could screw it. But one really convenient way that we have access to here is with a composite nail gun. And that's called a Raptor Nailer, and we resell those. And so those Raptor nails are great for holding down wood with a router, because if you hit them with the spindle as you're cutting out your part, it's all right. It's not going to damage your spindle because the plastic is soft and easy to machine. But it's also really easy to shear and take the whole part off when you're done. So it's very convenient. And we'll be putting that sheet down, putting some nails in to hold the remnants, and then the actual workpieces that we care about are going to be held in by those tabs we talked about earlier.
So it's useful when you don't care about how much of that work material you have left. It's an expendable as opposed to reusing
Right.
clamps. But you also don't have to worry about the area where the clamps take up. And
Exactly. There's no way
navigating
you're going
around
to, yeah, you don't have to worry about where the clamps are, whether or not you're going to damage your tool when you run into a clamp by accident. It just takes some of the mental equation out of it.
all right, let's mount that work material. Another aspect of routing that's going to be down to experience, choosing your end mills.
Right. So there's many different types of end mills. There's basically an end mill for every single different application. But we sell kits that have a pretty good variety, especially for beginner users, that's going to cover 90% of what you want to do. And in this instance, we're going to use a straight flute end mill for our contours and an upcut end mill, 2-flute upcut end mill for our drilling operations. And that's going to be a better end mill for drilling because it's got this upward twist, and that's going to pull chips up and out of the hole. So it's not going to sit there and just burn chips inside of that hole. But it's also going to kind of pull the top of that veneer up as it finishes, so you'll get a little bit of a fuzzy around that outside, and it's not quite as nice of a finish as you'd get with the straight cut bit, which isn't going to impart any sort of upwards or downwards forces on the sheet while we're cutting it.
That's just moving along the edge.
Right, exactly. So it doesn't clear chips quite as well, but it doesn't leave any sort of split surface on the top or bottom of the workpiece, unlike an upcut or downcut bit.
Is that specific to wood, or is that also with plastic and aluminum and stuff like that?
Plastic and aluminum, you see the same thing. It does make more of a difference in wood, especially plywood, when you're talking about separating plies from each other. But all the same rules still apply, and especially when you're doing fixtures, those same forces come into play. And if you have a fixture that is really strong laterally but not up and down, maybe you don't want to use a bit that imparts a lot of upwards or downwards force. It's always something you have to think about.
All right, guys, it's been a pretty long 3 days.
Yes.
It's why we're sitting. That's also because you made us these sweet chairs. Thanks so much, Drew, for coming by.
Yeah, absolutely. I mean, we're really excited to see what you guys are going to be doing with this machine.
I have a lot of crazy ideas.
Yeah, Frank, we've been talking a lot for sure about, I mean, it's a different tool in the tool set, right?
Yeah, another tool. There's never just one tool for every job, and this is going to make a lot of jobs really easy.
And the platform is massive. You have it set up right now, so it's 4x4 for wood, 4x4 for plasma, but you can shift that.
Swap it out, and I could make it 4x8 for wood or milling foam, or I have some crazy ideas for 3D things that I want to mill out of this.
What are people usually building when they buy a big router from you guys?
I mean, there's all sorts of things. We have tons of really interesting customers who make things from ice sculptures to submarines. We have first robotics teams using our machines, and as well as cabinet shops and people making signs and doors and even furniture.
And what are the requirements? Like Frank's shop is pretty well equipped to handle. You had air, water, power, but people have built these I've seen on YouTube in like in a shipping container.
Right. So you obviously need the space for it. You can find the dimensions online on our website. But you need a 30 amp breaker, 110 for the controller, for the electronics box itself. And then if you're going to run plasma, you'll need, usually depending on the plasma torch, it's about a 50 amp breaker and 220. And the VFD to run the spindle, which we saw this machine has, the 2.2 kilowatt air-cooled spindle, that's another 30 amp 220 breaker.
Yeah.
A lot of power.
Yeah, a lot of power, a lot
And
of
the
juice.
software you're using, you showed a little bit of Fusion 360,
Right.
the interface software.
So we usually we resell Vectric V-Carve products as well as Fusion 360. That's the suite that we point people towards. But whatever CAD CAM you're comfortable with is totally fine. We like to say it's an open platform, right? It runs G-code like any other CNC machine. We also resell Mach 3 as a generic CNC controller that runs on a Windows PC. But if you wanted to bring a different controller, you absolutely could.
Very cool. That CAD CAM pipeline, Frank, you have CAD guys here.
Yep, we are all soaking in all the CNC that we can.
We're going to have you stick around. We're going another project, so people out there can look forward to more projects using this Pro Series CNC from CNC Router Parts, and we're going to pick your brain more on CNCing.
Yeah.
Can't wait.
And I'm going to continue modifying this workspace to make this even better. We're going to get that hose up there the right way and get all kinds of things going on.
So thanks again, Drew. Thank you guys out there for watching, and we'll see you next time.